Ready to dive into something kind of fascinating. We're going to be tackling physics education in this deep dive. And not just the how, but the big why behind it all. Got a whole stack of research articles here, so should be interesting.
And we're going global with it, looking at classrooms around the world.
Exactly. Now, one thing that jumps out from these articles is scientific literacy as a goal. Sounds impressive, but what does that actually mean when it comes to teaching physics,
Well, it's about giving people the tools to actually use physics, not just memorize a bunch of facts, but use it to understand the world, making informed decisions about climate change, about new technologies. It's applying those physics principles to, real life.
So it's more than just acing a physics test. It's connecting those ideas to things that impact us every day.
Exactly.
Makes sense, but some of the research suggests that actually achieving that goal can be a little tricky.
Oh, it's a huge challenge. It's easy to say everybody should be scientifically literate, but turning that into something that works in a classroom is incredibly complex. There's even a lot of debate about whether those standardized tests, TIMSS and PISA, are actually measuring the right things even.
You've got those reports flagged. So what makes them so important for understanding this whole global physics education landscape?
They're like these little snapshots of what's going on in classrooms all over the world. TIMSS is really focused on how well students are learning the actual science content, the concepts, and PISA kind of zooms in more on applying that knowledge to, real world situations.
So two sides of the same coin.
Mm-hmm.
TIMSS checks the knowledge base and PISA sees if they can actually use it.
Yeah, exactly. But here's where things get interesting. Some of the researchers argue that TIMSS, because it emphasizes memorizing facts and formulas, might not be capturing the whole picture of a student's ability to actually think critically about, science.
So like judging a chef only on their knowledge of ingredients, not on the actual dish they cook up?
Perfect analogy. PISA tries to get at that by looking at application, but even then we're missing a lot of the context. Teacher training, what resources are available to students, those things hugely impact learning, but are almost impossible to compare across different countries.
Like trying to understand a whole symphony by listening to just one instrument. You might get a sense of the melody, but you're missing, the richness of the whole orchestra.
Precisely. And that's so important to keep in mind as we get deeper into the research here. We need to look beyond just the surface level of those assessments and try to uncover those deeper nuances of how physics is actually taught and learned all around the world.
Right. Those big goals of scientific literacy are important, but we don't want to lose sight of what's happening in those individual classrooms. Right. So TIMSS and PISA, valuable data, but just the tip of the iceberg, it sounds like.
Yeah. And speaking of different classrooms, ready to take a peek inside how physics is taught across different ages and different school systems globally?
Absolutely. Let's shift gears from the global tests and get a little more granular. Hit me with it. All right, so we're trading those global test scores for textbooks and maybe even some lab goggles. Where does our world tour of physics education start?
Well, buckle up because we're going all the way back to primary school. Remember those early years?
Yeah.
So much curiosity.
Yes.
Kids making their first discoveries about how things work.
Finger painting, building blocks. Was there really physics happening back then?
Absolutely. It might not be called physics officially, but those seeds are definitely being planted.
Yeah.
Think about it, kids exploring how things move, noticing light and shadows, experimenting with, ramps and building towers. That's physics in action.
So it's more about nurturing that natural curiosity and kind of setting the stage for more, formalized physics concepts later on.
Exactly. Now, in many English-speaking countries, you'll see physics woven into a more general science curriculum, often with some engineering thrown in. It's about getting hands-on, building things, and making those connections between, the ideas and the real world.
Yeah, makes sense. But the research also mentions something called Sachunterricht. Not familiar with that one. What's the story there?
Sachunterricht. It's a really fascinating approach you see in a lot of European countries, especially in Germany. Basically, it's all about breaking down those walls between subjects.
Okay.
Imagine blending physics with social studies, history, even art. It's about showing how physics is connected to, all these different aspects of the world.
So instead of just teaching physics as this isolated subject, Sachunterricht helps students see how it connects to, history and culture and their own lives.
Exactly.
It's pretty cool.
And it starts really early on. Imagine a class of primary school students learning about the buildings in their town. With Sachunterricht, they might study the physics of bridges, exploring concepts like tension and compression by actually building their own models.
That's a great example of making physics engaging and relevant. It's not memorizing from a textbook. It's about understanding how these principles actually shape the world. But what happens when students move on to, say, lower secondary school?
Things start to become a bit more formal. Students are tackling more abstract concepts. And this is where you see this global shift towards really emphasizing competence over, just rote learning.
So less about just memorizing formulas and more about understanding the why behind them.
Exactly. It's about giving students the skills to actually apply their knowledge, solve problems, think like scientists. They're designing experiments, analyzing data, using physics principles to answer real-world questions.
And it seems like there's a growing understanding that physics and math are like inseparable at this stage.
Absolutely. You see this big emphasis on what they call physical mathematical modeling emerging as a really crucial skill. Students are learning to translate those physics problems into, mathematical representations, solve those, and then interpret what the solution means back in the real world.
But they're learning a new language using math as the tool to unlock those physics mysteries. But that makes me think about the challenges too. What about students who maybe struggle with those math concepts? Does that hold them back in physics?
It's definitely a big factor. The research shows pretty clearly that a strong foundation in math is often really essential for success in physics, especially as you get into upper secondary school.
Makes sense. If you're struggling with the language, it's going to be tough to understand the more complex ideas. So what does this shift towards competence and application look like in upper secondary?
This is where things get really interesting because now physics education starts to have this kind of dual purpose. On the one hand, you're building a solid foundation for students who, are passionate about STEM fields, who might want to pursue physics at a higher level, future physicists, engineers, computer scientists.
Right, but it's also about preparing everyone else, too.
Yeah.
Giving them the tools to understand a world that's increasingly shaped by technology and, scientific advancements.
Exactly. Even if you're not planning to build a particle accelerator or design the next Mars rover, understanding basic physics is more and more essential in our tech-driven world, right?
For sure. And as we move up that educational ladder, the content itself is getting more complex too. We're talking about really diving into the details of energy, matter, forces, those core concepts that underpin everything else.
And it's not just about knowing the definitions, it's understanding how those concepts interact, how they play out in the real world.
So ready to unpack those fundamental physics concepts that students, really wrestle with.
Let's get granular.
All right, let's dig into those core physics concepts.
Right.
We've talked about like the what and the why of teaching physics, but what are those big ideas that students really seem to struggle with?
Well, there are a few that come up again and again: energy, matter, and forces. Those are like the cornerstones for understanding how the physical world actually works.
And it sounds like there's so much research into how students thinking about these things changes over time. Is it usually a smooth progression, or are there like common stumbling blocks along the way?
Oh, it's definitely not always straightforward. Students often come to physics class, with their own ideas about how things work, based on just like their everyday experiences.
Okay.
And we call those misconceptions. They might seem to make sense intuitively, but don't always line up with the actual physics.
So like thinking that a heavier object will always fall faster than a lighter one. I remember thinking that as a kid.
Exactly. That's a classic one that comes from how we experience gravity and air resistance in our everyday lives.
Makes sense.
But in a vacuum, all objects fall at the same rate, no matter how heavy they are.
Which is mind-blowing when you actually see it, right?
Right. And it really highlights how important it is to, challenge those initial ideas and help students develop a more, nuanced understanding. Like take energy, for example.
Okay.
It's this fundamental concept in physics, but it's also incredibly abstract.
Yeah, it's not like you can see it or touch it directly. Mm-hmm. It's all about like the ability to do work, to make things happen.
Exactly. And the research shows that students often have a really hard time wrapping their heads around the idea that energy can transform from one form to another. Remember those energy transformation diagrams?
Vaguely, yeah.
Yeah.
Lots of arrows and boxes.
Exactly. They can be a little much. But the key takeaway is that energy doesn't just disappear, it changes form. Like the chemical energy that's stored in a battery gets transformed into electrical energy that powers your phone.
Right, and then that electrical energy is transformed again into light and sound when you watch a video on your phone.
Exactly. And then, of course, some of that energy is always lost as heat, which is another concept that tends to trip students up.
Right. It feels like the energy disappears, but really it's just changing into a form that's not as useful.
Exactly.
So teaching students about those transformations and the fact that energy is conserved, that's key.
Absolutely. And then you have matter. What are things actually made of? How do we explain the properties of matter that we can actually observe and feel?
Yeah.
And that's where those microscopic models, those ideas of atoms and molecules and, even smaller particles become really important.
But those are so tiny.
Yeah.
It's hard to connect those invisible particles with like the large-scale properties of matter that we experience every day.
It is, and research has actually shown that that's a big area where students struggle. They can learn about atoms and molecules in theory, but then have a hard time explaining like why a solid object feels solid or why a liquid flows.
So it's about helping them connect those two scales, the microscopic and the macroscopic.
Exactly, like explaining how the way those tiny particles are arranged and how they're moving, that's what determines whether something is a solid or a liquid or a gas.
Okay, that makes sense.
And then, of course, there are forces which are all about interactions between objects. Now, a common misconception here is that students often think about force as something an object like possesses rather than the result of an interaction.
So instead of a moving object having force, it's about understanding that like force was applied to that object by something else.
Yes. Like a hand pushing a book across a table, it's that interaction.
Okay.
And that force from the hand pushing on the book is always met with an equal and opposite force from the book pushing back on the hand.
Right.
So helping students understand that forces always come in pairs, action and reaction, that's a really big part of building that solid foundation in physics.
It seems like a common theme here is helping students connect those like concrete everyday experiences with the more abstract, physics principles.
Yeah. It is. It's about guiding them as they refine their intuition, right? They come in with these ideas based on what they see and experience in their daily lives, but those initial observations don't always tell the whole story.
And that's where those physics practices that we talked about earlier come in. The problem solving, the modeling, the experimentation, all of that helps them, really refine their thinking.
Exactly. It's not just about replacing a misconception with, the right answer. It's about giving students those tools to think critically about their own assumptions, to use evidence to build these more, I guess you could say, sophisticated mental models of how the world actually works.
So it's not just about filling their heads with like facts and formulas. It's about giving them the tools to actually think like physicists, to question, to explore, to test their ideas.
Exactly. And those are skills that are more and more important as we all navigate a world that is so shaped by science and technology.
This deep dive has been fascinating. I mean, we've explored these goals of physics education, taken a peek inside classrooms all around the globe, really unpacked some of those big ideas that students grapple with.
And we've really only just scratched the surface. There is so much more to explore here. The role of technology, the challenges of teaching those more modern physics concepts, and the big question of how we prepare students for a future that's, so clearly going to be shaped by these scientific advancements.
And speaking of the future, here's something to think about. If physics is constantly evolving, how do we create learning environments that don't just teach what we know today, but also foster that, that adaptability, those critical thinking skills that are going to be needed to keep learning, tomorrow and beyond?
That is a big question, and there's no easy answer. But that's kind of the beauty of it, right? This pursuit of understanding. It's an ongoing journey, and we're all along for the ride.
Absolutely. Well, thanks for joining us for this deep dive into the world of physics education. We'll see you next time for another exploration into the world of knowledge.